So you got some material here, some uniform material and a uniform distance between here and here in some area, and we'll work area into this in a minute, okay? So you got this surface at temperature T1 and this surface at temperature T2. L is your distance from here to here, okay? And you have a constant temperature gradient. Temperature gradient temperature versus X, okay? Temperature gradient is dt dx. Okay? Now, between any 3 points, so here's the picture I just drew. Okay? You've got a heat flow, and this doesn't exactly fit the model we talked about a minute ago. You've got a heat flow from here to here to here. I'm sorry, from here to here to here. Okay? Heat flows from warm to cold. Okay? And we'll pull that together with the bug model. Yeah.
You're saying constant, steady state condition, being constant temps. You're saying T1 and T2 remain constant and they're not losing temperature?
Didn't understand every word, but it means dt dx is constant. It means if you have, it just means the slope of this graph is uniform.
Which means the difference between T2 and T1 is always going to be the same, regardless. That's what I'm understanding.
Yeah. Okay, well, as long as the difference is what it is, okay? So, dt dx is going to equal T2 minus T1 over L. And that's the slope of your graph. Okay? Now, the rate of heat flow per unit of cross-sectional area is directly proportional to the temperature gradient. Okay? Going to use Q for heat. So dq dt is equal to some constant. And K gets overused as constant. It has many different uses. In this case, it's going to be the thermal conductivity. And I'm kind of writing this out of habit rather than think about what I'm writing. This is dq dt per unit of cross-sectional area, dqdt, because it says rate of heat flow per unit of cross-sectional area, right? This is your rate of heat flow, and this is your unit of cross-sectional area, and that equals K times your temperature gradient. Temperature gradient is dt dx. In this particular case, dt dx, you have constant temperature gradient, right? It's this. Okay? And K is thermal conductivity. Depends on the material. And you can go to a table of thermal conductivity and find out what the conductivity of your material is. If it's steel, if it's concrete, if it's still air, as opposed to moving air, which involves convection and so forth. Okay?
Isn't air really poor?
I'm sorry?
Isn't air a pretty poor thermal conductor? That's why we use it for insulation.
No, air is a very poor conductor. Okay?
Is that because it's so non-dense?
Yeah. Basically, the thermal energy of one particle takes a while to transfer to another particle. Okay? Whereas in a crystalline structure, the disturbances more or less move at the speed of sound in that material. It's much higher. That's not a real good, that's not a rigorous statement, but it's kind of an idea. The speed at which disturbances propagate, which you get from the wave equation, right? Okay? And it depends on the stiffness of the material, just like the oscillations of a string or a rubber band chain or a paper clip chain or whatever, okay? Depends on the tension. I'll try to make those connections a little more. But this is what you have. So the thermal conductivity of a material can be measured. We just take a thickness of something and keep this side at one temperature and this side at the other temperature and measure how much heat flows just using a little bit of calorimetry. Okay?
Is cross-sectional area the area of, I don't honestly, the area of T1 and T2? Assuming they're...
It's the area perpendicular to the direction of heat flow. Just as in electrical conduction, it's an area perpendicular to the direction of the current.
So if heat flows in L, it's going to be a plane perpendicular to that.
Yeah.
Okay.
Yeah. So this thing has, the cross-sectional area in this case, well, you know, I said something about that earlier, so, okay, let's just say now this thing has a cross-sectional area, right?
Mm-hmm.
So there's your cross-sectional area, and it's perpendicular to the temperature gradient. Just as the cross-sectional area you use when you talk about current flow okay, is perpendicular to the direction of the potential gradient. And the potential gradient is what? It's the electric field. Okay? It's the rate at which the electric field changes with respect to position. That's what a gradient is, basically. Now you go into 3 dimensions and you use the del operator to calculate gradients and stuff, but only one of you has had multivariable calculus, okay? So it extends in a pretty natural way to 3 dimensions. Right now we've got to kind of confine ourselves to 1 dimension. So in a wire, your potential gradient, well, how do you get the electric field? You divide the change in potential by the length of a wire, right? That's just a derivative of your potential with respect to position along the wire. Okay? Totally analogous to this. And that's one thing I'm trying to do is draw the analogy here. The electrical analogy of this. Q dt, same as this, but now Q is charged, right? Okay? And it's equal to constant multiplied by V2 minus V1 over L, where now you have potential V1, potential V2, right? Potential is measured in what units?
Volts.
I'm sorry?
Volts.
What's a volt?
Work per Q.
It's what?
Work per charge.
Work per unit of charge. Joules per coulomb, right? Just to put it back in context. Don't tell me volts. I don't want to hear the word. If you use it on a piece of paper, you better note that this is joules per coulomb so you know what the heck you're talking about.
Like it's every time you say that.
Have I been talking into a vacuum for the last 3 months? No, I know I haven't, because y'all performed well on your midterm, okay? I'm just trying to keep you on track. Fair enough? Yeah. Okay?
I think it's just kind of funny because every time you say that, Elam says volts, and then Alexander turns around and says joules per unit charge, and just,
Work per unit charge. He said it right.
he said it right.
Now, the units of work are obviously joules, and the work of charge is coulomb, so it's joules per coulomb. But it's work per unit charge. There's your concept, right? So I'm glad one of you knows what the concept is. Everybody really does. Just make sure you go back to the unblameable concept, okay? Make sense? So this should make sense of this, and this should help make sense of this. Okay, what's your constant here?
Conductivity.
Conductivity, right. Okay? Okay, does that make sense? Halfway? You want to think of this analogy, because that helps you understand heat flow, but the mathematics is identical. So when you look at a problem in a chapter on heat flow, you already know what to do in terms of what you know from circuitry.